In this chapter, we are going to be looking at organizing and displaying our data. When data are collected in original form, we call it raw data or data. The frequency is the number of values that fall into a specific class of the distribution. And note that data is both a singular and plural word. Now, a frequency distribution is the organization of raw data in a table form using classes and frequencies, as you can start to see down below here and on the next pages. Now, there are some guidelines for choosing classes, and I've got some classes down here for a made-up data set, and every observation or data value that we gather must fall into one of the classes. The classes cannot overlap. They must be of equal width. There must be no gaps between the classes because we need to have a place to put all of our data. And even if there's no observation in a class, it must be included. We don't skip over any classes. Choosing the number of classes. If we have too many classes, it produces a histogram with too little information. Too few classes produce a histogram that's lacking in detail. So generally they say 5 to 20 classes is best. I say 5 to 10, maybe even just 5 to 8 is a better gauge. When a histogram contains an open-ended class, such as 100 and above, a histogram cannot be drawn. And that'll be the graph of the table that you create. Now, the most basic way of grouping your information is to use a tally method. And as different data values fall into the particular categories, you put a little hash mark, and then you put a crosshash every 5th term. Notice how all of my classes are of width 7. They go from 24, 31, 38, and I'm adding 7 to go to each lower limit of the next class. Now, if I take that same information and put it into another type of table, and I leave out that first column and only have the first list of classes along with the frequencies, that then is known as a frequency distribution. And that is the tabular, the table summary listing all the classes and their frequencies. So I would basically pretend that these tallies are no longer there in the second column. Now, I like to add up how many data values we have, and we have 3 plus 1, which is 4, plus 5 is 9, plus another 9 is 18, plus 6 is 24, plus 1, we have 25 data values in this frequency table. Now, if I leave off the middle column and I go with the first and the 4th column, that would be a relative frequency table, and that deals with the percentage or fraction of values falling into a class, usually expressed as a decimal. So in this relative frequency, in this next position, we'd say, oh, 3 out of 25. Well, that is 0.12. And then 1 out of 25, that is 0.04. And then we have 5 out of 25, that is 1/5 or 0.20, etc. 9 out of 25, that'll be a 0.45. And so by saying 0.45, we're saying 45% fall into that category. Finally, we're going to have 0.30 and 0.04, and this should always add up to 100% unless there is some rounding involved. And so if I only have the first column of the classes combined with the relative frequencies, the first and the 4th column, that would be a relative frequency table. Now, a cumulative frequency distribution is the frequency of items falling in each class that is less than or equal to a particular value. Cumulative means this value and below. When you look at your cumulative GPA, it's not just this semester, it's all of your semesters combined. Now, if I'm looking at cumulative frequencies, the name of the class actually changes. This first one would be X values that are under 30, and we'd have 3 of them. But then when I have an upper class limit of 37, I'm going to say, maybe that would be X less than or equal to 30. The next one will be X less than or equal to 37. And that's the 3 and the 1 beneath it added together, which is 4. And then when I go up to less than or equal to 42, we're going to add in 5 more values, taking this up to 9, then 18, then 24, and then 25. And by the bottom right corner, we should have all 25 out of 25 data values represented within the table. Now, a lower class limit is the smallest data value that goes into a data set. So for the first class, it's the 24 that's the lower class limit. And the upper class limit is the largest data value. So for that first class there, the upper class limit would be 30. Now, the lower class limit for a frequency distribution where we do not include the endpoints, well, I meant to have a less than or equal to type there. So that would be lower class limit 0, while the upper class limit is 4 because we're not including the 5. Now that would be if we're dealing with integers or whole number data. If we were dealing with money, then the largest value in that class might be 4.99, representing $4.99. It depends upon the type of data that we're dealing with. But while we're talking about frequencies, how many people respond in a particular way, you can't really have decimals because that tells you that half a person responded, and that doesn't make sense. And I say, if we do include the right endpoint, there will be an equal to on that boundary also, and that upper class limit would then be 5. Class boundaries are used to separate the classes so there's no gaps. The class midpoint, this is a formula, is found by taking the average of the lower class limit of that class with the lower class limit of the next class. So for example, when I have the 0 less than or equal to X less than 10, the next class is going to begin at 10 because the 10 was not included in that first class. The next class will be X less 10 less than or equal to X less than 15. So we're taking 0 plus 10, add them up and divide by 2, and that's where 5 becomes the class midpoint of that first class. Now the class width, by definition, is the difference between the lower class limit of a given class and the lower class limit of the next higher class. And so if I have this right here, the first class beginning with 10 and the next class after it would begin with the 20. That 20 is not included in the class above it. Then to go from 10 to 20, we subtract and we find that the class width is 10. The peak or high point of a histogram or a graph of these data sets is the mode. A histogram can be unimodal, uni being the prefix standing for 1, having 1 mode, bimodal, having 2 modes, or quite honestly, we could use the word multimodal if it's like a camel's back with a bunch of highs that are all equally high in several different places. Right now, we are only dealing with tables of information and some definitions of some class boundaries. As we move on, we're going to develop some other types of data. Now, at this point, usually if we were on campus, I would be taking a survey of the class asking you, how many fast food meals have you had in the past 14 days? And since I have to record this video ahead of time, I've made up some numbers. Actually, they came from a previous class, and I stopped at 25 data values in order to keep the numbers nice and clean. Now, the way I would go through and organize this information is I probably would begin with a tally method before anything else. And I'd start with this top row and I'd say, okay, or I'd start here, 0 less than or equal to x less than 5. That would be the 0 through 4s. And I'm going to cross them off as I find a 0 through 4. Here's 1, 2, 3, 4, 5, 6, 7, 8. I'm counting 8 of them. I could have put little tally marks as I found them, but I decided to count there. The next category will be the 5, 6, 7, 8, 9. So I'm looking for the rest of the single digit numbers. So I see this 8 beneath it a 6. So I'm going to count here and go, I'll go with a backwards cross. 1, 2, 3, 4, 5, 6, 7, 8, 9 values there. The next class would begin at 10 and end at 14. So I see a 12, an 11, a 10, and a 14. So that refers to 4 values. 15 through 19. Whoops, I skipped over the 13. Good thing I was paying attention there, because now I need to up that to a 5. Let's try this 15 through 19 again. I think I left off the 13 also because that was not crossed off. Good thing I am paying attention as I'm doing this. This is now up to a 6. Now let's go for the 15 through 19. You're probably shouting at your screen here. And I'm just seeing another 14 that I skipped over. My goodness, I'm having a bad day here. So this is now up to 7 data values, and I can cross off that 14. Now I only have 2 values left, namely the 20 and the 27. So those are going to be 1 each in those categories, and I'm going to put a 0 in the category that goes from 15 to 19. And as a double check, I'm going to add up these frequencies. 8 plus 9 is 17, plus 7 is 14, 17, 24, 25, 26. So apparently I counted something twice because I've only got 25 data values. And I'm actually glad I'm making these mistakes while doing this video with you, because I'm showing you how you can error check what's going on here by taking these multiple passes through the problem. My guess is it's this 7 is incorrect. So I'm going to go back and check my 10 through 14. I've got this 14, putting dots down there. 1, 2, there's my 11. Then I have a 13. Then I have a 10. Then I have a 14. And there is the 12. You probably were shouting out at me. And I think 1, 2, 3, 4, 5, 6 is the correct value for that position. And that's going to grab or change my value here to a 25. So notice what I did. And I'm glad I made that mistake. I used the grand total, knowing that there were 25 values inside that table, as a double checking system to make sure that I got those correct frequencies. Now, the relative frequencies says take these classes and turn them into a decimal. Anytime you see that word relative, you know we're dealing with a decimal. So I'm going to have 8 out of 25 as a fraction, followed by 9 out of 25, followed by 6 out of 25. We're going to have a 0 in this next category. Then we're going to have 1 over 25 and 1 over 25. Now, I'm okay with fractions, but technically we usually go with decimals. And since 25 goes into 100 4 times, I know I can go 4 times 8 is 32 and go 0.32. 4 times 9 is 36. That's going to be 36%. And by the way, you could divide these out longhand. 4 times 6 is 24, 0.24. And the last two should each be 0.04. 4% of the time in each of those categories, we got a response telling us we have this many meals out in the last 14 days. Okay, now we move on to a cumulative frequency distribution, and notice the category descriptions have changed because it's the under 5, under 10, under 15. Now these are frequencies, not relative frequencies. So I'm going to start with the 8 that was in that first category, and then I'm going to go and combine the 8 and the 9 together to get a 17. Then I'm going to take that 17, add 6 in, and that takes me up to 23. I then add 0 to keep it at 23. Then I add 1 for each of the next two categories, and the cumulative frequencies become 24 and 25. Now, if I create a cumulative relative frequency distribution, I'm basically taking all the values that are in this chart up here and dividing by 25. So I'm going to have 8 divided by 25, which is 0.32. Then I'm going to have 17 divided by 25, which is going to be 0.68. We can also find that 0.68 by taking the two relative frequencies up above and adding them together. And I could now take and add on a 0.24 if I wanted to bring this up to a 0.92. Or I could say that was a 23 out of 25. This will remain 0.92. Then we're going to add 4% in and get to 0.96. And finally 1.00, meaning all or 100% of my data values were below 30. Now this is a little bit tedious, and we're not going to be doing this a whole lot because we do have software that will do these types of charts for us. But what I want you to really understand is the difference between the names of these categories. When it asks for a frequency, you have a physical count. When it refers to a relative frequency, you have a decimal or fractional way of interpreting this. On a test, I will be asking most likely for decimals, and I will tell you specifically the level of accuracy, how many decimal places to round out to go. Generally, we will have a 4-place rounding rule in this class. 4 digits after the decimal, round to that position unless I tell you otherwise. I also want you to understand the word cumulative, meaning up to this point. Now we're going to turn our attention to the graphs of these different types of distributions. Now, a histogram, as you see listed here, is a graphical representation of a frequency distribution, and it differs from a bar chart, also known as a Pareto chart, in that there is a numerical scaling on the horizontal axis. This is a Pareto chart down below because there's no scaling. It's got Democratic, Republican, and other. Okay, when we do have scaling across the bottom, as we have in these next two pictures, then we are dealing with histograms instead. Now, when you are designing or drawing these by hand, you need to make sure that you are describing things properly. Notice we have titles on each of these. The first one is a frequency histogram, and it's got labeled on the vertical axis the word frequency, and we see physical counts going up the sides. Over here at the right, we have a relative frequency histogram using the same data. Notice it is labeled relative frequency, and we have decimals going up the side instead. Now I've got some comments down below, and I want to say that the shape of these two graphs is the same, but different information is being portrayed. On the left, we can see physically between the 60 and 70 and that tallest bar, 10 of the short-term investments fell into that category. we actually have counts. And reading back from this diagram, you can see how many data values were represented. We have 3 plus 1 plus 8 plus 10 plus 7 plus 7 plus 4. You could add those together and know how many investments were analyzed in making that graph. Whereas over at the right, instead of telling you there were 10 values, a frequency of 10 in that tallest bar, we only know that 25% of the values fell in that category. Okay, we don't know if that's 25% of 20 data values. We don't know if it's 25% of 4,500 data values. Okay, that way we cannot go back and recreate the data set. We only have percentages falling into different categories. When you have a large number of data values, you don't want to do a frequency histogram because you might have big bars going up into the thousands. Whereas over here, this handles large data sets very well. Different situations, different data sample sizes will probably dictate your choice of the type of graph that you want to give. But notice the shape of these two is exactly the same. It's just the scaling on the vertical axis that is changing. Here are some other examples. Sometimes we use what's called truncation marks. Notice on this first one, we didn't have the ranges from 0 to something. It's just 0, school-age children and family. Well, if you put the bar between a 0 and a 1, you don't know what that really means. So we straddled this across the 0, and the next bar going up really truly represents the 1. And since you don't have the ability to draw a vertical axis, a y-axis, right through this 0, we put little truncation marks to say, hey, we've taken a snippet, we've taken some scissors to that x-axis, and we've kind of messed with the scaling a little bit. And so that's what's happening here. And again, we've got a frequency histogram and a relative frequency histogram of this problem. Now, sometimes you have categories where, just like here, it's above where the 0 was the value when you wanted to go up. Now I've got 5.5 to 10.5. That probably represents the data values from 5 to 10. And the next category, which says 10.5 to 15.5, would be the 11 through 15 category. And because it's a range of values, sometimes we go 0.5 below and 0.5 above. Again, you will probably never be drawing a graph of this type, but I wanted you to be aware that this does exist. And sometimes the software you use will create boundaries that look like that. A frequency polygon basically takes each of the bars in a frequency histogram that you might have drawn. Let me switch to my pen here. And it plays connect the dots with the top center of each of those different bars. So instead of drawing those bars in there, we have the dots representing the top center of each of those little places. I can take this middle one and put a dot right at the top of each, and those would be what we would connect. And that becomes a frequency polygon. A cumulative frequencies, cumulative means it's growing, growing, growing. And notice up here, if there were 20 pieces of data here, 20 would be the height in that far right bar if we go all the way across. We can have a relative frequency histogram, which is the same picture that's at the left, but notice along the side we have percentages instead. And if you take a cumulative frequency and change it to a cumulative relative frequency, that actually has a name called an ogive. You will not be responsible for drawing ogives for me in this class, but I want you to know what they are. Now, other types of charts. We're familiar with the bar charts. We're familiar with the Pareto charts. A time series graph allows you to see how the data has changed over time. And it turns out that we always put time on the horizontal axis, so we can see as time goes on from left to right what the fluctuation is going to be. It's always on the horizontal axis, earlier on the left, more recent on the right. A pie chart is a circle that we divide into sections to represent things. Notice that this has a title. Notice each of the different pie slices is labeled not only with the name of the category, but with the percentage that goes with it. Now, you can do these using technology where usually you have an Excel spreadsheet, you type your numbers in, you go up to a command that says, I want to create a pie chart, and it will do it for you. And that, in fact, will be one of the activities that you're going to do for me in this class, and there will be another video covering that topic. When you are doing this by hand, first off, you have to be able to draw a circle. Take a cup or something and put it on the table and draw a circle around it, or use a compass. And then as best as you can, find the center of that data set, or the center of the circle, and put a dot there. Now, what I like to do, and I've drawn these dots, and I don't usually have these dots here, but I like to represent the 4 cardinal directions, north, south, east, and west, because as you can see in this diagram, it breaks the circle into 4 equivalent sectors or quadrants. And usually we can eyeball things pretty well there. And then what I would do in my head, I try to break those 25% slices into 5 parts. So let's see how well I do. Here's 1 slice, 2 slices, 3 slices, 4, and then 5, and they're about the same size. And that way, if I need a 30% slice, I can go 5% and then straight down. Now I have a 30% slice right down in that section. And if I need a 5% slice, I can just add in a piece like that, and there's 5%. We don't really like drawing these by hand because they get kind of sloppy. Software really is the way to go for something like this. And that's why I'm going to have you do an activity that asks you to create some of this using some software, because that's a skill that is really a valuable skill to have. A few fun comics. To encourage healthier eating habits in the workplace, all pie charts are to be replaced with organic arugula charts. Okay, not too funny there. A stem and leaf plot is a data plot that uses part of the data value as the stem and part of the data value as the leaf. So I have 40 data values here. The context isn't important, but basically we use the tens column as the stems and the units digit as the leaves. And so when I read this first row, it refers to the 3 data values, 38, 36, and 39. Basically, I'm grouping all the 30s together. And there was only one number in the 40s, which was 47. And a whole bunch in the 50s, as you can see, reading through that chart. Now that is just a regular stem and leaf diagram. If I take that same data, but then amongst the leaves, put all those leaves in numerical order, then we have what's called an ordered stem and leaf diagram. Sometimes you want to use these stem and leaf diagrams to compare 2 data sets, and what we have is a back-to-back stem and leaf plot. So I can have 2 cities like I have here, Atlanta and Philadelphia, and I've got the numbers in Atlanta to be 27, 28, 26. I read it in the other direction, and on the right I have a 25. Likewise, I can read all the different values in the 30s in the next row and the 40s in the following row. And this is a way to compare 2 data sets. We can ask ourselves, which data set is more skewed, which data set has a larger range, things along those along that line of reasoning. And you'll see questions like that when we move into the next chapter. Okay, sometimes we can, when it's not easy to do it the way we had a moment ago, we can have a 2-digit stem. That's what the first one that I'm pointing at right over here. The first row with the 19 would refer to the 190s. The 20 would refer to the 200s, then the 210s and the 220s, and only the units digit would go in the leaf position. Or I can take all my 190s, all my 200s, 210s, and 220s and split them into 2 rows each. And that gives us a different visual display. It's the same information in both of these, but sometimes you find something interesting. Now, when you do split them up, one of the rows contains the 0 through 4, and the next row contains the 5 through 9s. We use the rules for rounding, where 0 through 4 says to round down and 5 through 9 says to round up. We use that to determine which row or with which stem each leaf decides to go. These are tools for you. They basically help you to see the shape of the data and to get a good feeling for the spread of the data. So if you have a weird data set that you need to organize in your own way, then you're allowed to modify these as fits your needs. Here's another one where I took this data set and I've got a single digit stem of 50s, 60s, 70s, 80s, and 90s, and then I split it into dual stems. Now notice something interesting appears in the bottom graph. Notice how in the lower 60s, I have a blank there. Now, you might say, wow, why do I have that in my graph? Well, I do want to keep that blank there because it shows me some separation. It shows me that the 58 that is in the row above it is actually spread apart. It's separated from the next lowest value, which is 66. Now, I don't see that in the graph above, and to me, that's an important characteristic of this diagram. So we do want to keep this blank there in the lower 60s. Now, as far as the lower 50s go, where there's no data beyond it, there's no reason to keep that 5. So I would cross that off potentially. But I wanted to show this to you as yet another option and show you where maybe it's a good reason to have that blank in there. Now, don't put a 0 in that blank because a 0 would represent the number 60. We just leave it blank, saying there is no data here. Now let's turn our attention to the different shapes of data sets, okay? We've already talked about tables and graphs and different types of formulas to help you learn about observations, but now we're going to focus on shape. What we have here down below, the shape of a bell curve, is really the ideal situation, as we're going to see. And I've got for you 8 different shapes. The ones that we're going to be using the most in this class, are going to be the bell-shaped curve, and then the left skew and the right skewed, followed by the uniform. We won't deal so much with the J shape and the reverse shape. Bimodal, we have 2 values that are the highest there. That's why it's bimodal. Then we have a U-shaped graph. Now, what I do want to call to your attention is when your data set is right skewed, it tapers off to the right. When something is left skewed, it tapers off to the left. So it is the direction of the tapering that is identified in the name of that distribution or shape. Sometimes we call the right skewed distribution a positively skewed distribution and a left skewed distribution as a negatively skewed distribution. When you go on to a psychology class, the concepts are all the same, but sometimes we change some of that vocabulary around. And former students have come to me and told me that some of the classes in psychology at our school are using positively and negatively skewed instead of right or left skewed. Now I got a key fact down on the bottom of your page there that says if a random sample of a large enough size, we're not really saying what large enough is taken from a population, the shape of the distribution of the sample will approximate the shape of the population's distribution. And the larger the sample size, the better the approximation tends to be. Of course, with the caveat that we've got a good sampling method. So if we have a distribution that is definitively skewed to the right, okay, then when we draw our sample data, we would expect that it will be skewed to the right also. This is a key fact that really underlies a lot of the future mathematics that we need in this course, and that's why I introduce it to you at this point in the course. Now let's talk about misleading graphs, and this is kind of a fun topic to deal with. And the first one is that of improper scaling. And I want you to just look at this picture here. They're trying to talk about tobacco taxes up, and it's going from 39 to $1.01, 39 cents. Well, that's about 2.5 times the size. When you go from 39, it doubles to 78, then you tack more on, about 2.5 times bigger. Well, does that rectangle they've got drawn there look 2.5 times bigger? That's kind of strange there. I think all of the bars going up should have equal width, and then we should have it 2.5 times taller. I think the height is right, but to increase the width also really messes with you. Can be misleading. Now, lack of scaling or truncated graphs is another category. Both of these two charts dealing with passenger traffic at the Denver airport purport the same information. Now, when you look at these, the top graph, it looks like, yeah, there's a general slight increase over time. And the next one looks like, wow, the airport really is gaining a lot more traffic. But I want to call something to your attention. If you look at the scaling here, the bottom scale starts at 47. So if I start this graph at 47, notice what we're seeing. Only the top stuff that's in the rectangle that I've isolated is being blown out of proportion in this bottom graph. Now, technically, that's not fair advertising. The one that's on the top here is a more realistic picture. However, we do allow this bottom graph if we throw a couple things in. First off, technically, they should put in some truncation marks on the vertical axis so that you know it doesn't start at 0, or to at least call your attention to that. Also, when you look at this, technically, they usually will draw in a hairline fracture on these bars, so you can tell that they've been cut at a certain point corresponding with the truncation mark at the left. Now, when you put those little marks in, as I have done, technically that passes the legal muster for being truth in advertising. And I'm using air quotes around the word truth. It is generally one way that you see rather frequently of people misleading others in the types of graphs that they draw. Ideally, all the charts that we look at start at a 0 in the bottom left corner, so the relative scaling is appropriate. Now, I've got a couple other examples here. The next one is well, I guess that's a histogram here where I've left out a couple categories because there is no data. And the comment I want to make is we don't just leave I mean, we don't just skip it and smush the graph together so we don't see the gaps. We let the reader define or decide on their own why there might have been a gap in the information. We just don't exclude it from the data set itself. Another problem is to compare these two jets, and we're talking about cost of jet fuel increasing apparently, because in 2013, that picture of a jet is getting larger. But the question is, how much larger? Now, I've drawn some rectangles here that are just about the size of that jet. And you might ask, how many jets of that bottom type or the left type will fit into the one at the right? Well, if I line it up with the top there, just about there, and then I connect the dots, I can see or connect the rectangles, I can determine how many rectangles wide this drawing is. It looks like it's about 3.5 rectangles wide the way I've drawn it. And then height-wise, well, it's not twice as tall, and it's a little bit not 3 times as tall is being a little generous. So I'm going to say it's about 3.5 times wider and about 2 3/4 times taller. But when you think about that, that doesn't mean, oh, 3 times bigger, because the way, if you were to look at this as a rectangular grid, it kind of looks like area-wise, the second picture is about 9 times bigger. Notice how if I just enlarge it, and I'm not doing a super job here, but there's 9 times larger. And then even then, a little bit more. So I'd probably say 9.5 times larger, but they meant to just make it 3 times larger. Likewise, if I were to look at these two squares and I were to say, how many times bigger is the larger square? Well, area-wise, 4 of the small squares could fit into the large square. But what have we done? We've doubled the length, we've doubled the height, and since we've doubled each, 2 times 2 is 4, the area has quadrupled. And that right there is the same problem that we saw if we go back to this newspaper article with what is that? The tobacco tax. They use that same example incorrectly right there. So I wanted to call it to your attention. I'm not wild about graphs involving pictures. Here's another misleading graph. We've got the same data. Notice the left one doesn't start at 0, it starts at 3.14. So if I were to take a look at this picture at the right and start it at 3.14, it might be right about that. I'm only emphasizing the top portion of this graph, zooming in on it. And over at the right, it looks like it's a fairly steady graph, but over at the left, they have accentuated this rise to make like it looked like interest rates are really rising rapidly each year when they're not going up by that much at all. So again, notice the graph at the left is not starting at 0, but it also doesn't have truncation marks or hairline fractures inside of those bars. So it is a misleading graph. Here is a chart that was found online, the same data 2 different ways. The one at the left looks really nice. It's easy to read, but notice that the green slice for 10 million is about the same size as the blue slice for 85 million. Now, we can't just change the size of the pie slices. Over here at the right, now you can see how small the 10 million slice is in comparison with the 85 million in the blue slice. It should be an 8.5 times larger slice because it's 8.5 times times the money rate that we're dealing with here. So scaling is important because you're changing the impression. On the left, it looks like that gray area is half of the data, but over at the right, you can see that it's really 65% of the data. Here is an example that I took off of Amazon. It just happened to come from August of 2020, and it just happened to be the daily special where they were advertising some pickleball paddles. And notice the regular price that's been crossed off is $70. And the special price rounding off is $53. So you're looking at and they're saying, oh, you're saving $17, which is a 24% saving. So looks pretty good. And then they've got this graph down below here, and it doesn't even show you 24%. If you're just looking at this graph, it looks like, oh my gosh, this bottom portion of the graph down here at the bottom right seems like it's like almost a 70 or 80% drop, but it isn't. But I want you to notice over at the bottom left, it doesn't start at 0. They were accentuating what they wanted you to see. Now I'm going to take this entire graph and move it upward, and I have already extended by hand drawing this graph all the way down to 0 where it really should start roughly, and I put little tick marks every 10. And now you can look at this and say, ah, this is how far it's dropped out of the full-on drop out of this much. And now you can see the 24% isn't as big of a drop as they had made it appear to be by truncating off the bottom portion of that graph. So my hope is that through this video, it hasn't just been an experience of this is how you draw a graph, but I hope that you are finding out these are ways that people can mislead you in looking at a graph, and through understanding those ways that you can be misled, you will be better consumers in looking at the graphs.